And for me, say that because I copy paste it. Pretty much, I just people. Excuse me. Yes, well, in the one from the last class. Well, I mean, I haven't done the activity, but we didn't start.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. I'm a little bit sleepy today. My dad called me and woke me up this morning at 7 o'clock. He's on a cruise right now, so he's on a boat that's going from Miami to Portugal. And he left my mom behind, so it's just him and his 3 bros. And so he called me to tell me how much fun he's having and how much alcohol he's drinking, how much food he's eating. So I'm like, great, Dad, it's 7 o'clock in the morning. I'm really tired. It's like, okay. So yeah, I'm a little tired, but yeah, I'm glad my dad's having fun. Okay, so first order of business today. I think everyone probably noticed yesterday the midterm project scores went up, so you should be able to go on Canvas and see your score. I also attached the rubric so you can kind of see how I kind of graded you on certain sections. Just like kind of like I've been doing on the activities, I did try to leave as many comments as I could to kind of explain you know, kind of my reasoning in terms of, you know, why I took points off in certain areas or certain areas I think you did really well in. So definitely read those comments because, you know, the final project is going to be very similar to the midterm project. So, you know, what I'm looking for is that, you know, a lot of you did really well in the projects, but, you know, I think everyone had at least some areas in which they can improve. So, you know, I am going to look to see, you know, if you know, for the final projects, if you do include your major areas. Okay. So definitely check out your midterm project scores. If you have any questions on them, or if you want some clarification in terms of why you got a certain grade, definitely let me know, and I'm always open to discuss that with you. Okay. Now the other thing that we're starting today, well, it's assigned today, is your final project. Okay. So final project is going to be due on Monday, May 19th. So that is a week. That is the Monday after final week. It's actually the day of commencement as well, and so you know, actually on that Monday, I probably won't be available too much for questions because I will be at commencement. But you know, you guys have about a month to work on it, and the final project is going to be what you're going to see very similar to the midterm project. So I wanted to spend kind of the first 15 minutes today talking about the final project, what's different about the final project, And then we'll kind of launch into our lecture for today, which is on verification and validation. Okay. All right. And so from here on out, this class is, there's a lot that we can cover in this class still, but a lot of it kind of has to do with kind of more advanced features within ANSYS itself. And so after today, so today's kind of the last day of topics that I really want to cover for everyone. But from here on out, if there's a particular topic that you guys want me to go over, definitely let me know. And so I do have, quite a few handouts and quite a few lecture notes that are available on the website. And so if you want me to go through any one of them during the lectures, I'm always welcome to do that. The only things that are set from here on out are just the last two activities. So we have activity 7 for next week, and then activity 8, which is kind of the, on the second to last week of the semester. And so besides those, a lot of this semester is up in the air. And so I encourage you guys to kind of look and see what's available on Canvas in terms of my handouts. And if there's a particular one that you want me to go over, just let me know. And we can cover that in the class. Or if there's something that you want me to cover about ANSYS, maybe something that you are interested in learning, maybe you heard about a certain feature, or maybe you're working on something for work or for research, let me know. And then, I can probably prepare something, maybe not for this next week, but maybe for the final week of the semester, I can get something ready for that time. Okay. All right. Any questions on anything before we get started for today? Okay. All right. So let's start with the final project. Okay. So just like the midterm project, the goal of the final project is to perform a full finite element analysis and to write the corresponding technical report. Okay. So there's a lot of similarities to the midterm project. There's just going to be kind of a couple extra components to the project, as well as a little bit extra flexibility. Okay. So the biggest change that you'll see here is that you have the ability for the final project to choose a geometry of your choice. Okay. So if there's a particular geometry that you're working on for work, or maybe something for your research, or maybe something for a project that you're doing, you are free to choose that for your final project. So you're not just going to be limited to what I have chosen for you. Okay. Now I would like you to run it by me, and so don't just really quickly make a cube on SolidWorks and say, like, I'm doing a project with this cube. Can I do this cube for my final project? A cube is a little bit too simple. So I would like it to have some degree of complexity. You can use the midterm project geometries as kind of a reference in terms of kind of what I expect. But it should be kind of worthy of a finite element analysis. Okay. And so if you're not sure, if your geometry has enough complexity, just send me an email, just send me some screenshots of the geometry, and we can kind of talk about it. Okay. Okay, but if you don't want to choose your own geometry, there is a choice for you. And so there's a reason why I gave you 2 choices for the midterm project. And so if you don't have your own geometry that you want to analyze, you can choose one of the midterm project geometries, but you have to choose the one that you did not choose for your midterm project. So you can't just do the 4-way valve twice, or you can't just do an office chair twice. And so you have to make sure that you choose something different from that. Okay. Okay, so first order of business for the final project is to choose your geometry, either something of your own choosing, or one of the ones that was available for the midterm project. Right? Okay, and so from there, the project requirements are going to be very similar. So there's going to be a project objective. So a lot of you guys did really well for the final project, but I think a lot of the comments that I left for people was make sure that you think of your objective and kind of make sure that's the focal point of your analysis. Okay, to make sure you kind of are thinking about that. Methodology for the most part is going to be the same. So you're going to have meshing, boundary conditions, material properties. Make sure you do your mesh convergence test. And so there were a few people that didn't include the mesh convergence test in their report. So make sure you do that for the final project. Okay. Okay. Just like the midterm project, you're going to have 3 static scenarios, and so 3 different conditions on the boundary conditions, 3 different loadings, 3 different constraints. Okay. Make sure that your loading conditions are unique, right? And so just merely changing the magnitude of the loading that does not constitute a different scenario. So make sure you're changing either the direction, or maybe you're adding an additional load, or you're just changing the constraints entirely, okay? All right, so all of that is so far is exactly the same as the midterm project. Now, one thing that's going to be different about the final project is that I want you to include at least 2 of the advanced process features that we've gone over in the activities since the midterm project. So, for instance, you can add a transient simulation. So that's activity 5. You can do design optimization. That's activity 6. Modal vibration analysis. That's activity 7. Buckley analysis, activity 8, okay? Or any of the additional kind of, ANSYS handouts that I have. So for instance, thermal simulations, a fluid simulation, maybe an anisotropic material, that's a popular one. We may go over that one. And so I want you to include at least 2 of these advanced features within your report, in addition to the 3 static scenarios. And so in total, you should have kind of 5 different scenarios or 5 different simulations that you're going to run for your final project. At least 3 static simulations and 2 simulations, or at least 2 advanced features of this. Okay. And one thing that I'm going to be grading you on is you want to make sure, or you should make sure, that whichever advanced feature that you choose, that it makes sense relative to the geometry that you chose and to the problem objective or project objective that you chose as well. Okay, so don't just pick the 2 easiest ones. It's usually very obvious that you pick the 2 that were the fastest, but sometimes it doesn't make sense to do a transient analysis. Sometimes it doesn't make sense to do a modal analysis on a part, right? So you want to make sure that the reason that you're picking these advanced features actually gives you some information that's going to be useful for your geometry, for your project objectives. Okay. Okay. Any questions on this so far? Yeah.
What about fatigue life?
Fatigue life, that's one you can do as well. Yeah. So I do have a handout on that one too. So if there's a handout on it, if we talk about in the class, it's all disparity. Okay. Good. All right, so next is the ANSYS results. So these are kind of more or less kind of the same as before. The additional part to this, of course, is that you have to show some results from your advanced features. So, your transient results, or your modal results, or your fatigue life results, thermal results. So you want to make sure you show that in your results section as well. Okay. Discussion section, mostly the same. There are a couple additional questions here. And so, for instance, I want you to explain how you would verify or validate your simulation results. And so that's kind of the subject of the lecture today. And so make sure you address that in your discussion. Okay. And then the conclusion is same as before. Okay. Template, I posted a report template. This final project obviously is going to be a little bit longer because there's some additional things you have to include in the final project. But on average, most people's reports end up being about 16, 20, maybe 25 pages as well. It depends on how big your figures are and how many figures you include. Okay. But don't, this is not a requirement. So, just kind of write as much as you need to. Okay. The rubrics posted online as well. It's an individual project, so there's no working on teams. And yeah, and that's it. So, not too much to explain with the final project, very similar to the midterm project. Just be aware of the kind of additional requirements, and and just be aware that you can kind of choose your own geometry. Okay. Any questions on the final project? Okay. All right. So definitely, get started on it. If you have a I know a couple of you have kind of already asked me about geometries before. So just run it by me one more time. Yeah, if you have questions, just ask. Oh, by the way, so the due date, this is about as far back as I can push it, and so just make sure that you're aware of that deadline. So I can't really push this back any further because I do have to finish grading by that week, and I have 2 other classes with finals that I have to grade as well. So yeah, so with this due date here, you'll have basically all finals week to work on it, the weekend after finals week to work on it, and even a little bit of that Monday as well. So remember, it's due at 11:59 p.m. on that Monday. Okay. Okay. And in case you were wondering, Like I mentioned earlier today, that, the rest of this class here is gonna be kind of whatever you guys want me to kind of talk about. If you wanted to see kind of the selection of different handouts, of the selection of different kind of topics that I have, you can check it on the Canvas site. So from the Canvas site, if you click on the Files tab here, you click under Lecture Notes. Okay. These are all the lecture notes that we've covered so far in the class, right? And you can see here that the lecture notes end on lecture notes 15, which is buckling, analysis, and stress stiffening. But I have all of these other handouts down here. So A1, A2, A3, A4, A5, and A6, right? So all of these are, valid topics that we can talk about in the class. So if you have a particular preference, there's a particular one you want me to talk about. It sounds like, I think I should talk about fatigue life analysis. And so it sounds like that's an interest of the class. Just let me know and I'll fit it into kind of the next couple of weeks. But if there's something that you want me to talk about in ANSYS that's not covered here, something that you want to learn, definitely let me know as well. And then I can prepare something, maybe for the final week of the class. I'll prepare a handout and lecture notes for that as well. Okay, all right, so let's go ahead and switch over to the iPad. Okay, there we go. Okay. So the subject of the lecture today is, so far, in this class, we've mostly focused on just kind of the ins and outs and the details of using ANSYS as a software to get finite element results. Okay. So today's lecture is going to be a little bit different in that it doesn't directly have to do with ANSYS. In fact, it doesn't directly have to do with finite elements or using finite elements in general. But it's an important topic that I feel like has to be covered in every single kind of computational modeling class in general, and that is the topic of verification and validation. Okay. All right. So what is verification and validation? So verification and validation have to do with the fact that, when you run a simulation, when you run a finite element simulation or just any simulation in general, CFD, finite difference equation, right? At the end of the day, what you're simulating it's not a reality simulator, right? And so, a lot of times what you get from a simulation is going to be different than what you are going to observe in reality. Okay. So let me explain. So, so far, we've seen that finite element simulations can be very powerful tools when you're doing engineering design and analysis. So the ability to kind of take an engineering design and virtually apply loads and constraints to it and predict outcomes is very valuable because that saves you kind of the effort of kind of building these parts, in the physical world, saves you time, saves you money, right? But, where FEA kind of derives its power is in the fact that, we trust an FEA simulation to be an accurate representation of, what would happen in reality. So when we take our CAD files, when we take our CAD models, we load it into ANSYS, apply a force and apply a constraint, right? We observe things like the deformation, the equivalent stress, you know, we trust, or, you know, what we hope is that, you know, if we were to kind of build this part out in reality and apply the exact same loads and constraints, we would observe the exact same results, okay? And a lot of times this is true, right? And so if you set up your FEA simulation properly, just like we've learned in this class, you know, the results that you're going to get are going to be a close representation of reality. But of course, you know, this is not always the case, right? Oftentimes you can use a computational tool, and the results that you get from the tool, you know, does not necessarily mean that it's going to be replicated in real life as well. So anytime that you are, you know, running a simulation or even just solving an equation, right? So if you think back to, you know, all of your theory-based classes where you have, you know, an equation, a mathematical equation, differential equation that represents some kind of realistic phenomenon, you know, that simulation or that equation is a model for that physical phenomenon. So what is a model in this context? So a model is something that gives you a prediction of some kind of real life phenomenon without actually having to observe it in reality. That's the whole point of FEA is to simulate these things so, you know, we don't have to go and build these parts ourselves, right? So the interesting thing about models is that, you know, when I think when people are first introduced to this concept of a model, you know, people naturally kind of think of things like ANSYS or think of things like, you know, maybe differential equation, right? These are models that have been kind of tried and tested and kind of, you know, developed and refined so that they are a good representation of reality. But, you know, there are a lot of good models out there, but there are also a lot of bad models out there as well. Okay. Let me give you an example. Okay, so let's consider kind of a very simple structural problem. So let's say that we have a cantilever beam. Right, so we have a beam that's fixed to a wall. And let's say that we're applying a bending force to it. So let's say that we're applying a force F right at the end of the beam. Okay. And so in kind of very typical form for this class, you know, let's say that we want to compute or we want to predict the maximum amount of force that this beam can withstand before breaking. Okay, so obviously, this is a problem that you want to do with the model because you don't want to build a cantilever beam and possibly break several of them to find the maximum value. Okay. So how would you approach this problem, right? And so if I were to give you this problem right now and say that, I want you to solve this, probably everyone in this class would open up answers to, first of all, model the beam, apply boundary conditions to the beam, and then you're iteratively going to change the value of F until you see that until the equivalent stress in the beam, matches that of the yield strength, right? So that's approach number one. Okay. That's probably the first instinct for everyone in this class, hopefully, right? Well, let's think of another approach, right? So how else can we predict this beam failure? Okay, so what's another way that we can predict this this beam failure, right? And kind of maybe think outside the box of what a model actually is, right? So let's do really outside the box. Let's ask my 5-year-old nephew what he thinks of this problem. Actually, technically, he's not 5. He's like four. He's 4 years and like 10 months old. So he's turning 5 in a couple months. So they say like Oliver, like what do you think of this, right? So we have this beam. We'll say it's made of aluminum. How much force can this beam withstand before before breaking? And I asked him this question. So I saw him over the weekend, and so I asked him. I said, Oliver, what do you think of this? What was his answer? He said, you know what? I'm turning 5 in a couple months. F is 5, right? And I said, 5 what? 5, what is that 5? And he said, it's 5. And I said, 5 what? He said, 5 dinosaurs, because he's really into dinosaurs right now. So, obviously approach 2, maybe not as accurate as ANSYS, but it is still a model, right? It fits the criteria of a model, right? So it's a way for us to predict the results of this problem without having to actually build it ourselves, right? But obviously, one of these approaches is going to be better than the other ones, right? It's the cousin, no, or it's the nephew, no, it's ANSYS, right? ANSYS is the better model in this case. Right? So this one's pretty obvious, right? So this one is obvious, which one is a better model than the other ones, right? But this kind of raises the question of how do we determine or what are the metrics or how do we basically decide which models are better than other models in certain situations. Turns out, there are certain methods that we can do to assess the reliability and accuracy of our models, and that is verification and validation. And so anytime that you are taking a course or you're learning about new computational tools, you should always kind of ask the question or think about kind of verification and validation. Okay? And that's kind of the subject for today's lecture, maybe a little bit of Thursday if we don't finish. Okay. Any questions on this so far? Okay, all right, so let's give some definitions. So, let's talk about, what these actually mean. Because oftentimes people get them confused with each other. Okay, so let's start with verification. Okay. So the definition of verification is the assessment of the numerical accuracy of a simulation relative to the solution of the underlying mathematical equation. I'll write it down. So obviously, this idea of verification has to do with, strictly has to do with numerical techniques, right? So finite elements is a technique for solving differential equations. Same thing for finite volumes and finite differences. Okay? So anytime you have kind of a computational code, ultimately the purpose of that code is to solve for a solution to these differential equations, without having to actually solve them by hand. Okay, so verification basically asks the question of, are you solving these equations correctly? All right, so verification is interesting because verification has actually nothing to do with kind of the real life phenomenon that we're looking to model. So that's actually has to do with validation. Verification is more about, did we write our code correctly? Do we set up our equations correctly? Is our mesh fine enough? Okay. So one aspect of verification that that we've been doing in this class for a while is this idea of a mesh convergence test. Because depending on the refinement and depending on the size of the elements in your mesh, right? The software is either going to have an easy time or a difficult time solving the underlying equations, right? So that's kind of the main thing that you're testing for with the mesh convergence test, is to make sure that your mesh is refined enough, your elements are refined enough, you have the appropriate element order, that you're solving the equations correctly. Okay. Because the main thing that occurs is that if you have a coarse mesh, is that you're increasing the amount of numerical errors or numerical discrepancies in your solution. Okay. So verification, this is something that, you all are doing, with your, with your projects. By making sure that the mesh has enough elements to solve the equations. Okay. All right, any questions on this so far? Okay, good. All right, so that's verification. We'll talk a bit more about that. So what you'll see is that verification, for the most part, you don't have to do, because that's verification is a task for the developers of a finite element code. So all the employees that work at ANSYS, it's their job to to verify the code to make sure that the equations are solved properly. Okay, next is validation. Okay, so validation is the assessment of the accuracy of the mathematical model relative to the observations of the real life phenomenon that it's attempting to model. And again, I'll write it down. I know that was a mouthful. Okay. All right, so every time you run a simulation, we're attempting to emulate or we're attempting to simulate some kind of real life phenomenon. Okay. So validation is, asking the question is, are we simulating this real life phenomenon accurately? Okay. And sometimes it's a question of, are we even solving the appropriate amount of physics in this situation? Okay. So a good way that I think of validation, or kind of the question that you should ask yourself, is that, are we solving the right equations, or did we set up the problem correctly? All right, so validation is actually a much more difficult question to answer. But ultimately, that's the one that we want, for our simulations. And so, the probably the most common issue with validation is just, proper setup of the material properties and the boundary conditions. And so if you don't set up the material properties correctly, or your boundary conditions are incorrect, you don't properly constrain the model, or you constrain it in the incorrect place, your load magnitudes are off, or the direction of the loading is off, right? You're going to get results that are not consistent with reality. Okay. Okay. So verification and validation, this is something you should be thinking about for every single one of your simulations, right? Because if your simulation is not an accurate representation of reality, effectively it's useless, right? And so it's it's not getting the right results then it can't be used for design, it can't be used for analysis, that, all it's really good for is just kind of just a pretty picture. Which is not that useful for most contexts. Okay. Any questions on validation, just the definition here? Okay. All right, so together, verification and validation we kind of form a very important kind of basis for a lot of finite element simulations. Okay, but in reality, the vast majority of verification and validation is actually not performed by the users. And by the way, I don't think I've mentioned this, but a lot of times I'll shorten verification and validation to V&V just because it's shorter, right? So the vast majority of V&V is actually the responsibility of the developers of the finite element code, the developers of the CFD code. So they are the ones developing it, and so they have to be the ones that to prove that, first of all, that there's no bugs in their codes, that the equations that they're solving them correctly, so they have to perform verification. But also, that the equations that they are solving, these are accurate representations of reality as well. Okay. So as a user, this class is focused on mostly using finite elements. The development class is 541. But as a user, you don't have to worry about V&V. In fact, if you're using a software like ANSYS, where you often have to pay a lot of money to use it, part of what you're paying for is that you're paying for the trust, you're paying for the reliability that ANSYS has done a lot of these tests for you. So the reason you have to pay thousands of dollars for ANSYS, or usually not you personally, but your company has to pay thousands of dollars every year to use ANSYS, is the fact that ANSYS is very thoroughly tested. It's updated and checked for bugs on a regular basis. It's validated on a variety of different test cases, and so that's kind of what you pay for, right? And so you kind of pay for that trust, and you pay for that reliability, that you can use to present your results. Okay. So we'll touch a little bit briefly in terms of what kinds of tests that's done, but I wanted to mostly focus on there are still things that you still have to do as a user to verify and validate your results, so that people can increase trust in your simulation. Okay, and that's kind of what it's all about. And so, the whole purpose of V&V is to increase trust in your simulation results, right? And that was a big theme for the midterm project, right? And so a big part of your projects is to thoroughly explain your thought process, your modeling decisions, your meshing, your boundary conditions, so that people can trust the results that you are publishing about in your report. Okay, so V and V is just another avenue, another way for people to increase trust in your results. Okay. And to a certain point, V and V is a requirement, right? Because, one thing that you've probably noticed so far in ANSYS is that it's very easy to take any kind of CAD model and run a simulation on it and get some kind of results, right? Whether those results are accurate and whether those results are reliable are a completely different story. And so kind of the onus is on the user to say that these results, we got them, we paid for this very reliable software, so that's a big part of it. But I've also done these additional things, additional tests to assure you, the reader, that my results can be trusted, they can be reliable. Okay, so that's kind of the focus of this this set of lectures. Okay. All right. Any questions on this so far? Okay. All right. So let's talk about some let's talk about some examples of what you can apply. Okay. So let's dive into verification a bit more. Give me a second. Hey guys, can you quiet down in there? I'm teaching a class over here. Okay, let's talk verification. All right, so verification, remember, is testing to make sure that your code is solving the equations correctly, right? So let's talk a bit about kind of how a developer of FEA would be able to do this. So again, this is usually not something that you're going to do. I mean, you can do this if you're curious. But one way that this typically done is to solve what's called a test problem or test case. Or benchmark, excuse me. Okay. So a benchmark test is usually a suite of different tests that you can do with a very clearly defined solution or result. So let's say that you're developing your own finite element code, you're open sourcing it. That's very, very common nowadays, and so you'll see a lot of research softwares or even just personal hobby projects that are aiming to write their own FEA codes for certain situations. Okay, one of the first things that you're going to do just to make sure or to kind of get people to trust that your code is legit is to solve a benchmark case and show that you get this well-known result. Okay. All right, so one example that I've worked with, it's not really directly related to this class, but in the world of optimization, since we did that last week, there's a very famous problem called the Rosenbrock problem, which is famously very difficult to kind of get the optimal results for. So it's a mathematical equation, it's a set of equations that has a result that's normally very difficult to obtain. So if your code can replicate the exact solution or the exact result of the Rosenbrock test, then your optimization algorithm kind of passes that kind of first test. Okay. But again, this is something that's already been done by the ANSYS developers. And so this is something that you typically don't need to worry about. So you don't need to run ANSYS through the benchmark tests. There are benchmark tests for finite elements. ANSYS has kind of done that for you. And if you ever are interested in kind of developing your own FEA code or any computational tools in general, benchmarks are probably one of the most useful tools that you can use to make sure that your code is working correctly. Because I will say that, as most of the time, when you develop a code, it's not going to work on the first try. In fact, for a code that's as large and complex as these finite element codes are, there's probably, a ton of bugs within the code that you just didn't even realize. And so, benchmark test is a good way for you to kind of, sift through those bugs and fix them to make sure that you're getting the right benchmarks. Okay. Okay. And I'll leave a note here too that, if you are ever interested, or if sometime later down the road, you are going to be using a different software other than ANSYS. Maybe you're using an open source software and open source code. You want to make sure that you check if the code is well verified. So a lot of times, if those open source projects are in a place where they're publishing, then they've probably run a decent amount of benchmark tests. But it's always good to check just to make sure that your code is the open source code that you downloaded randomly from the internet is going to get the right results. Right? Okay. But again, that's mostly for developers, and so as a user of finite element, you're not going to be worried about benchmarks. But as a user, you want to make sure that you're running your own tests to make sure that the equations are being solved correctly. And like we mentioned before, the primary way that you do this in FEA is through a mesh convergence test. Okay, so let me draw a typical mesh convergence test. Okay, so for your typical mesh convergence test, on the horizontal axis here, we have number of elements. Vertical axis here, we have some quantity of interest. So let's say that we have deformation or stress. And so what most of you have observed, in your project is that as you refine your mesh, your quantity of interest will eventually converge to kind of its true value, right? So you might have a situation that maybe converges like this. Okay. So we've talked about mesh convergence tests within the context of justifying the number of elements, right? And so if you have a mesh convergence test like this, and let's say that you chose this as your mesh, right? Right. And so at this point right here, you can say that further refinement of the mesh is not going to lead to any improvement of the solution because the solution has converged, right? What that means is that, for regions or for meshes that are to the left of this, right? And so if we look at, if we look at the mesh over in this area of the mesh convergence plot. Up to this point, we've said that, our mesh isn't refined enough here in order to get an accurate solution. Okay? But we never really talked about kind of why that's the case. Okay? So the reason that's the case is that, between those meshes and eventually the mesh that you pick to converge, the underlying equations and the boundary conditions and the material properties, none of those are changing. They're all staying the same, right? But what's happening is that if you have a mesh that's too coarse, your elements are not fine enough, then it's really difficult for the software to get an accurate solution to the underlying equation. So that's kind of the main reason why, we do the mesh convergence test is that, in order for finite elements to work, in order to get an accurate solution to the underlying differential equations, your elements need to be small enough. And so if the elements aren't small enough, then your simulated solution starts to deviate from the true solution of the underlying differential equations. Okay. Okay. So mesh convergence test is, something that, you should do for every finite element study. And that's mostly to minimize the numerical errors that come from a coarse mesh. Okay. All right. Any questions on this? Okay. All right. So that's all I want to say about verification. Okay, so we'll start talking about validation, but we'll probably finish our discussion on Thursday. Okay, so remember, validation is the process of taking your simulation results and proving that your results are an accurate representation of reality. Okay. Okay. Now, validation is a lot more tricky, and so verification. You can think verification is actually quite easy because you can do all of it within the code itself. Oftentimes, if your code isn't well verified, you either have to fix a bug somewhere or you have to refine your mesh. So that's a lot more easy to do. For validation, you're asking the question of are my simulation results, are they an accurate representation of reality? So in order to actually prove this, you actually need to compare your simulation results to your real life scenario. And that's hard to do. And so, you have to set up a situation that kind of, where you're able to, first of all, do an experiment where you can observe and record all the data, as much data as you can. But then also, simulate that exact same thing in the finite element simulation. Okay. So the most common way to do this, and kind of the gold standard way to do validation, is to do what's called a validation experiment. Okay, so the idea with the validation experiment is that you're going to be doing a physical test, and so this is a test that you're going to do in reality, right? In a controlled, kind of usually laboratory environment where you can observe and record a lot of data on the results. Okay. Okay, so for example, let's go back to our cantilever beam from before. Okay, so let's say that we set up a cantilever beam experiment within a lab. Okay, we have our cantilever beam. And then we apply a force onto the beam. Just like we did in the example at the beginning of class. Okay. But we're going to do this in a laboratory. So once we apply the force, we'll have measurement kind of equipment in place to measure something like how much does this beam deform. We're going to measure the physical deformation. And maybe you've set up other probes on the cantilever beam as well, right? To measure something like the strain. Right, so the idea is to run a physical experiment, get as much data as you can, right? In certain locations, and so it's going to be impossible to get data on every single location. But try to get as much data as you can from this experiment, right? Then what you're going to do is you're going to simulate the exact same scenario, so the exact same physical dimension, the exact same loading, the exact same constraints within your finite element software. And the idea with doing that is you're going to try to replicate the exact same results or the exact same data or measurement that you got from the physical experiment. Okay, so within ANSYS or whatever other finite element software you're going to be creating a CAD model for the beam, applying the loads digitally, and seeing if the deformations that you observe in your simulation, maybe you measure deformation at the tip, you're going to see whether that matches up with the physical experiment that you ran in the lab. Okay, so ideally, they should match. Right, and for a relatively simple case like this, I expect it to match. I shouldn't expect, there shouldn't really be any discrepancies in this case. For relatively simple cases, there usually isn't a need to validate because, they've probably been validated, many times before in ANSYS. The interesting validation cases are, some of the more maybe research cases or niche cases, or, maybe a new application that you haven't seen before as well. So this happens a lot in research applications because, usually when you're doing research, you're looking at kind of a new problem or a new type of application, right? And so you want to make sure that the results that you're getting are, good, right? So just because ANSYS is validated for a cantilever beam, usually doesn't mean that the software is as reliable for a new kind of application, right? So I'm gonna give you an example, so you don't have to write this down. This is kind of just my own experience. So a lot of my past work has to do with running simulations of blood flow. And so the idea or kind of the problem of validation comes up a lot because blood flow is very complex, it's very complicated. And doctors, medical doctors are all very smart people, and they are not very trusting of the engineers. And so one thing that we're constantly having to do is to validate our results to basically show that what we simulate is a good representation of reality. So one of the projects that I worked on was validation of blood flow simulations in the coronary arteries. So those are the arteries that kind of snake around the heart. And so what we did was that in certain patients, we the doctors took a catheter and they measured flow and pressure at certain locations within the branch of the person's coronary arteries. And then what we did in simulations is we tried to run a simulation and replicate those exact same values of flow and pressure, completely blinded to the results. And so, we ran our simulations without really any knowledge of what the flows and pressures should be. And I will be honest with you, the results were not good. So we did not do a very good job of predicting the flows and pressures. And so, we published the paper, but just because we put a lot of work into it, but yeah, there's still a lot of work to be done within that area itself. So George, I know you asked a question. Is there a way to predict if blood will clot? That is a very interesting question that is very open at the moment. So blood clotting or coagulation is very difficult to model. And so biologists and engineers have kind of been wrestling with that problem for decades at this point. And so some headway has been done, but there hasn't been a definitive mathematical model that can really accurately predict blood clotting, just because it's so multifaceted and there's a lot of different factors that can affect clot. So right now we're not at a good stage, and so computational tools for blood clotting are kind of in the very early stages, and so they're kind of where finite elements was maybe 30-40 years ago. So yeah, there's still a lot of work to be done in that. Okay, so that's the ideal case. And so ideally, if you wanted to validate your simulation results, you want to validate your code, a validation experiment is kind of the best way to kind of go about it. Okay, any questions on validation experiments? Okay, all right, so last point that I'll leave you with before we head out for today is, what if you want to do validation and you don't want to run an experiment, right? Because validation experiments are nice, but they're also very costly and time consuming to do. And oftentimes, you're running a simulation, you're doing it for a case where it's literally impossible to get the physical measurements anyway. So let's see, is it possible to still do validation without a physical test? All right, so thankfully the answer is yes, and so it is possible to do validation without an experiment. Okay, oftentimes these types of validations they take the form of trying to replicate some kind of test case that's within the literature. So let's say that there's a certain problem that hasn't been that's been studied before, but no one has run simulations on it before. And so if you want to apply finite elements or any kind of simulation to that scenario, you could try to replicate that case study as much as you can and try to replicate those results as closely as you can. Okay. So in this case, in spirit, it's very similar to the validation experiment, except that you're not the one driving the experiment. Someone else has already run it, they've already published their results, and you're trying to replicate those results within your simulation. So this is actually quite common, especially in the areas of kind of new applications. Just say adjust. Sometimes, if you're not getting good matching, sometimes it's as simple as just changing the boundary conditions or making sure your mesh is fine. But in the worst cases, you have to go into the code and actually modify it to maybe account for certain types of behavior that you didn't account for. Okay. Right. Okay. So all that is good, if you're developing a code or you're doing research, but what about the average user, right? So what if you're just an average user of ANSYS, do you have to do validation? So for your final projects, for the midterm project, is there any validation that you can do for those cases? Because most of the time, when you are going to be running FEA, as a design engineer or analysis engineer in a company, right, you're not going to have access to physical tests. In fact, if you ask your manager to run a physical test, they're going to look at you like you're crazy. They're like, they hired you to avoid doing the physical tests, right? So is there a point to doing validation, or is this something that the average user has to think about? And I would make the argument, yes, right? While you're not going to be, you're not going to be running the physical tests, to validate your results. It's still worth it to look at your results and analyze your results and do what I like to call sanity checks on your results. The worst, the cardinal sin that you can do, if you're going to work with computations of any kind, FEA, CFD, is to just trust your simulations right out the box, right? And so you should always have a critical eye or skepticism, in terms of, do these results make sense? Did I set up everything correct? Right? And so, the most basic thing you can ask yourself is, do my results make sense? Look at the magnitudes of the deformation, the magnitudes of the stresses. Think about those, look at those relative to the amount of loading that you put in. Look at the directions of the deformations. So do all of those things make sense, right? You'd be surprised. And so, there are, when you start to work on FEA on very complex cases, you may misplace a certain load, right? So maybe you don't put a load there that should be there, or maybe you suppress a load that shouldn't be suppressed, or maybe you put a load in the opposite direction of what it should be, right? And so first thing to ask yourself, do your results make sense? Are they what you expect, right? that's why I ask you at every single activities, to do a prediction of what you think the results will look like, because that's going to help you kind of, curate your results and make sure that, you set up everything correct. Okay. Another thing that you can do is you can compare your simulation results to another type of calculation. So usually like a simplified calculation. Right, so maybe you solve a different equation, a much simpler equation. So maybe you do like a back of the envelope or back of the napkin type of calculation, right? Usually I tell people that, if you didn't have FEA, if you didn't have ANSYS, what kind of calculation would you do to help you with this design or help you with this analysis, right? And then compare that result to your FEA result. And oftentimes, you can think of some discrepancies in that case, right? So maybe you ran your simulation, you're like, all right, these results don't quite make sense. You do some kind of back of the envelope calculation, and you're like, okay, that should, change things. And so, always check your results. So always. So don't trust your results right out the box. You should always kind of question your results to see if they truly make sense. Okay. Okay. Any questions on this before we wrap it up for today? Okay, all right, so we actually did finish the verification and validation, so we'll start something different on Thursday. Remember, take a look at the list of handouts on Canvas and see if there's anything that you want me to cover in particular, and I can cover that in the class. But I think what I'll do for Thursday is that, I'll start to cover fatigue life analysis, because I think, there's some interest for that. Thursday, we'll go over fatigue life analysis. I think next week we'll do our next activity, and then, we'll go from there. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you all on Thursday. Good.
So I'm going to be
Okay.
now going to actually
Okay. That looks good. So I mean, you think about different ways that you could class and stuff. And it looks like that box is kind of designed.
Yeah.
And so okay, yeah, no, I think that sounds really good. So you can probably apply like activity 5 to that.
Yeah. I'm not asking tomorrow.
Okay. Yeah. No, I think that's going to be.
Oh, Professor, I have a quick question. I don't know if you can hear me.
Yes.
Oh,
Hey, Brianna.
so like when comparing Helm calculations to like a finite element analysis or CFD, would there be like a huge discrepancy between the two if it's like something simple compared to something more complex in the 3D model?
Yeah, so if you are going to do like another calculation, a simple calculation, most likely there is going to be a discrepancy because you're kind of simplifying out a lot of the complexity in the design or the geometry or the conditions. So it's really hard to replicate that complexity in kind of a simple calculation. And so in that situation, when I say compare the results, you're probably not looking to match the results exactly. But you are going to try to, you're probably going to want to glean some qualitative information or maybe some trends that maybe your simulation is not picking up. And so, for example, let's say that you're running an FEA simulation on a very kind of complicated geometry, but it's not quite bending the way that you think, or or the stresses are not as high as you think. And so maybe what you can do is you can run a calculation. Apply the loads in a flat way and see if you get kind of the same magnitude or the same kind of ballpark of the deformations and the stresses. And if not, then that may give you some information on how you can kind of fix your finite element simulation. But if they are kind of in the same ballpark, maybe that is the result. And so that can happen sometimes too, where maybe your result is maybe not what you expect, but it's still correct.
Oh, okay. Thank you.
Yeah, no problem. Yeah.
I know.
I do, yes.
That's.
So that is A5. Well, you could do aerodynamics, but the one that I have here for fluid is internal flow, actually. So like pipe flow. That's too much.
Concept for aerodynamics.
Yeah.
You change it a bit.
You do need to change it. So for aerodynamics, usually you're gonna do like an external flow. So you're gonna, instead of, well, for internal flow, basically you have your object and your flow is contained within the object. For aerodynamics, usually you're gonna put an object in kind of a bigger flow unit, and the flow goes around the object. And so some similar concepts, but the way you set it up is actually a bit different. So,
Okay.
but yeah, same, but you know, we can go over this if that's something that you want to.
Yeah, maybe, yeah.
Okay.
I like that.
Okay,
Thank
all right.
you.
Yep.
If you choose valve, can we implement this on the valve table?
You could, yeah, you could. Yeah, so the valve is actually empty. So you would have to modify the geometry a little bit, because you would need a mesh of the inside. We'll talk about that if we do. Probably I'll do this one, not next week, the week after next, but next week we have to do but yeah, you actually need a mesh of the fluid part. So, but there's a way that you can load your geometries into like SolidWorks, and you can do what's called an inversion of the geometry. So you can get a mesh of just the inside part.
I was gonna ask, are these two models done in design modeler so they can be optimized?
Yes. Actually, no, they're in the other one, SpaceClaim. But SpaceClaim should interface with design optimization, with the design optimization as well. It's just probably the way that you specify the parameters is a little bit different. Yeah, but because it was made within ANSYS itself, you should be able to do optimization.
And impact factoring, the impact analysis is considered like the advanced mechanism.
Yes.
Right? Okay.
Yeah.
Thank you.
Mhm.